In this video, we look at a quick example, I hope, of one interpretation of a double integral, and that is the mass of a particular region. Okay. The description in this problem is giving a description of the region itself. Okay. We have a region in the xy plane. Okay. We can see we're going to be in the xy plane. We see all these formulas involving x's and y's. Okay, we have the line y is equal to negative x. Okay, y is equal to negative x is a line that passes through 0, 0, but has a negative slope. And then we also have the parabola x is equal to y minus y squared. Okay, we can notice that this problem factors as 1 minus y. So if you look at the zeros of this function, ask yourself when is x is equal to 0. That would tell you that x would be 0 at y is equal to 0 or y is equal to 1. So we have y being 0 at y is equal to 0 and y is equal to 1. All right, now we need to figure out which way the parabola opens. Notice that y is equal to a half is a point between 0 and 1. It's a y value between 0 and 1. So let's find the x value when y is equal to a half. So when y is equal to a half, the x value is 1/2 times positive 1/2, which is positive 1/4, which says that if this is x is equal to 1, that our x value when y is equal to a half is positive 1/4. So the parabola is right here. And it also tells you that since there's a minus y squared, that the parabola is essentially going to open to the left. And we have finished just a sketch of this region. So it's a parabola that must do something like this. Okay? And we now want to find the mass of the region enclosed, so this region itself. Okay? And we know that the density function is equal to y. So we're going to do a mass integral of the region R, and we're going to assume that the density function is y, and then we need to figure out how we want to order this integral. What order do we want to set this up in? And I'm seeing that we would like to set this up as a dx dy problem because we have the same function on the left and the right if we go from left to right. So we can see here that we're going from x is equal to negative y up to x is equal to y minus y squared on the right. So this is our left function, and this is our right function. And it's the same function no matter what value y is on the left and the right. Okay, so that's why it's advantageous to choose the dx dy ordering. And then we can see that y goes from 0 up to y is equal to, and we're not sure yet. Okay, so we need to figure out what is the y value of intersection. Okay, so we can see that x is equal to y minus y squared, and we can also see that x is equal to negative y. So we want to figure out where these two functions intersect each other, and that will tell us that y squared minus 2y has to equal to 0. So factor out the y. So y is equal to 0, which is one of the values of intersection. And then we can see here that the other y value of intersection is y is equal to 2. So we'll put a 2 here. And that is a setup of the mass integral. Right? We can evaluate this integral. I won't bore you with the details of that. It's a pretty straightforward integral to compute. So let's do palette. The hard part here is getting the integral set up. I will evaluate this integral so that you know what value you're shooting for. Right? We know that we're integrating a density function y. We've chosen the dx dy ordering. Y goes from 0 up to 2. X goes from negative y on the left to y minus y squared on the right. Okay? And that integral evaluates to 4/3. So the mass of this region is 4/3, probably kilograms, maybe whatever the units are. Okay? You know that you've got the right region, right? Let's see if we've set this integral up correctly. Region plot, right? We know that x has to be bigger than negative y, and x has to be less than y minus y squared. But we know that y has to be bigger than 0, but had to be less than 2. So this is a description of that region. And let's plot this from, say, x going from, say, let's see, when y is equal to 2, the x value is 2 minus 4, so that'd be negative 2 to 1/4. And then y goes from 0 up to 2. So if we have this region of integration done correctly, we should see that this region plot looks like what we have sketched over here on the right. And as promised, there it is. Okay? So ends this example of using a double integral to compute mass. We've also practiced setting up integrals, choosing the correct order of integration, and the evaluation step, this 4/3 is what you can work towards.